what I have in the model. I have a footing, uh, a pad foundation by the section properties footing one. So take a look at footing one and define section properties slab section just to see what we have for this footing. For footing one, we have a footing used C35 concrete grade, and the depth is 550 millimeter. And I'm trying to just follow whatever we had in the example 622 from the book. This is the footing I'm trying to model in SAFE. So the depth was 55 centimeter. So I'm just following the same properties in the example of the book. So we can take a look at the material as well, C35, and the material is here, define material, C3540 is here, and it's very important here to put 35 megapascal here for the characteristic concrete cylinder strengths, FCK by Eurocode. So I just changed this to 35, and here we are. Also, if you right click on this footing, you will see that the underneath has strings of ASPR1. And this is a sort of spring that if you go to the spring property, area spring, it's a distributed spring, and ASPR1 has the characteristics like 20,000 kilonewton over cubic meter, and it is compression only. I will talk about the other options here later in a separate video, but for now I stick with the compression only for this, and this is the subgrade modulus 20,000 kilonewton over cubic meter. You need to maintain it for your coursework based on soil type B of the Eurocode, as I discussed last week during the lecture. So if I press OK, this is my pad, and I have the bottom of my column definition here as well. It means that I'm modeling the column here with the certain dimensions. So it is a sort of section properties is stiff one. So I want to model the column on the pad foundation because it's a at least in this area, it's a constraint for the deflections of the pad foundation. So if I go to again to the slab sections, and for the stiff one, if I modify it, you can see that it is a kind of slab that has 50 centimeter thickness. So it means that I'm putting some half a meter of the superstructure bottom column onto the pad foundation. So it's a kind of the kind of modeling that incorporates here half a meter of the column. So it is something that connected to the pad foundation, and in this area the pad foundation is not free to move somehow. It's semi-restrained. So it is more realistically modeling the actual structure that we have in reality. So we have two slabs, one for modeling the column, one for modeling the pad foundation. And in addition to those, I have, if you select this perimeter line, you can see I have one strips selected. So I have defined this strip based on draw design strips. I've used this one just to create this strip, and this will be used for the design purposes. And what the program does is it sums up all the internal forces in this box for the design purposes. I also have two strips here, one here and one here. These two strips help me to have a node here to be able to put the loading on it. So if I right click on this node, you will see that in terms of load, I have minus 800 kilonewton for the dead load and minus 300 kilonewton for the live load. And in both cases, the dimensions of applying this load is 375 millimeter, which is in agreement with what I have in example 622 of the book. So I have my load here. I have the column. I have the pad foundation, and I have the springs, and I have the pre-meter strip definition. Now I'm ready to analyze my model, and it will take a few moments. However, I just take a look again at the results of hand calculation in this example. If you see the external force, I mean the internal moment is 329 kilonewton meter here, 329 kilonewton meter. However, when I run the model, okay, this is the displacement, but if I go to display and show forces for the strike forces and in the load combination 2, which is 1.35 dead plus 1.5 live load. If I go to show the moment, this is the moment in the slab. And as you can see, the maximum is 322 rather than 329 of the hand calculation. It's less than that. There are two main reasons that these are different. However, they are in very good agreement and they are somehow close together. However, first of all, we are accounting for the flexibility of the foundation, of the pad foundation here. On the other hand, the hand calculation assumes that the pad foundation is a rigid one. In addition, we are modeling the column in the middle, which suppresses the moment distribution at the middle, which should be maximum, you know. For example, this is the distribution of moment in this line. And as you can see, in the place of the column, the moment doesn't go up. If you remove the column here, the column simulation here, this will not be capped and it goes upper. So anyway, they are very close together and we can rely on this for the design. And if I go to design for concrete and start design, it will design the necessary the rebars for me. But before that, if I go to the define and I have here, section properties for reinforcing bar sizes. I have deleted all of the bars because they are American standards, and I have added the bars, the European bars. So you can see that these are the names and these are the bar diameters. So this is the area. So from number 6 to number 50, we don't use number 50 really, but most commonly we use 20, 22, 18, 25. These are really the most common used rebars. However, we can go up to 28, 32 if we need. But I have these definition here. I just imported them. Don't worry if I'm just locked. My model is locked now, but you can just import it very easily. And now I've designed my section, my path foundation, and as you can see, the maximum bar can be reached here like 800 square millimeter. So it was in the hand calculation, it was something like uh, yeah, something like 800 square millimeter. However, for the crack control, it was increased to 1,000, almost 1,010 square millimeter. And the result was bar number 16 at each 20 millimeter, 200 millimeter. And if you go for the detailing and for the concrete detailing, if you start slab foundation design check, you can go for detailing. And here is the geometry of the foundation. And if you this is the footing number one. So if you open the footing number one, you can see that in this case for the safe, the design consists of rebar number 20 at each 300 millimeter. So almost the amount of reinforcement is in a very good agreement with the hand calculation. And because everything is symmetric, we have these reinforcement at both sides, X and Y. So it's a kind of mesh. So if you view it 3D, you need a sort of symmetric mesh at the bottom of your pad foundation, and that's the ultimate design for this pad foundation. In addition to the design and obtaining the reinforcement, you can take a look at other responses of your pad foundation, like this shows the support or spring reactions. For example, you can see it in load cases or load combinations. The worst case obviously is the load combination number two. And if you take a look at FZ, that the others are zero because they're just a spring, vertical springs. So if you go for 3D, you can see these are the strip, the soil, the underneath soil reactions, those springs underneath. It's a distributed area spring. However, it uses the distributed area subgrade reactions to come up with some individual springs distributed along the pad foundation. And as you can see, they are all in compression. And you can see, for example, soil pressure in terms of uh, combination number two. So if I go again to the plan, we can see this is the distribution of soil pressure. So the maximum is probably here, like something around 285 megapascal. And this is not megapascal, it is kilonewton over square meter. And you should see that how the soil can carry this one. You know, you should have the soil strengths and compare this value with the soil strengths. As I said, if you have soil type B from the Eurocode, if you go through the geotechnical books and handbooks, you can see there are some values for the soil bearing capacity. So this should be compared with that one. In the example, it's not mentioned, so we don't need to do this for the example 622. However, for the coursework, you need to have subgrade reaction plus the soil pressure allowance stress, that stress that it can carry. And this maximum stress should be compared with that one. So if I just save this and I will talk about moments in a separate video. For now, it's enough for this video. Thank you.